So the recording has started now. Now I'll share my screen. Hello everyone. This is NPTEL CS52 Spring 24 Reinforcement Learning Course by Professor Balaram from Computer Science Department in IIT Madras. And I am Sandarbh from Computer Science Department in IIT Bombay. And this is the week 12 of PMRF TA session. And this is being held on 16th April 2024, which is Tuesday. So today is the last session. Like there won't be an extra session, at least from me. Maybe some other TA might be having it. So last session, and anyone who has taken this course can attend. Again, the discussion on practice assignment, problem solving, doubt clarification, and two-way communication. These are the main reasons to attend these sessions. And expectation is that you should have watched the weekly lecture videos for week 12 this week, which was from DP. From DP, just like hierarchical reinforcement learning, is an advanced topic. So whatever like main RL part was there, like it was till week 9, and 10 and 11 were in hierarchical RL, and then 12 in Form DP. So these are more like advanced topics, and you should have at least made an honest attempt on weekly assignment and practice assignment. Again, certain and Batu like doesn't cover these content, HRL and Form DP. So there will be papers, and I'll link some popular websites for PoundDB in today's reading section. And as usual, slides and recordings will be made available in the same Google spreadsheet. So guidelines as usual. The order will be practice assignment, then problem solving. This will contain problems which are not part of practice assignment and assignment. Demo, today we will have demos on POMDP. Like I won't go rigorously into the demo because not much content has been covered for POMDP. But either way, like we'll have three demos. And the first one will be regarding a tiger problem. So I'll introduce the problem and describe how to do it using POMDP. Then in second one, we will tackle a grid problem. And third one, like this will have obstacles also. And third one will be a usual carpool problem. And then finally, we will discuss the assignment. Okay, so these are the big 12 topics: POMDP introduction and solving POMDP. So let's begin with the practice assignment 12. So first question says that suppose that we are solving a POMDP using few MDP-like solution discussed in the lectures, where we assume that the MDP is known and solve it to learn key values for two state action pairs. Then which of the following are true? So we can recover a policy for execution in the partially observable environment by weighing Q values by the belief distribution. It is denoted by this notation BEL, so that pi s is equals to argmax of A, and this is the summation over states, and this is weighted by this belief of status. Like what is the belief that we are in status, and correspondingly like Q value corresponding to that state and action, and we will take the argmax over actions, and whichever action has the highest this entity, then we will take that action. This will be our policy. So this is the correct option, right? And second option, either way, like it's single option correct. So first means that other three cannot be correct. But let's see that we can recover an optimal policy for the from DP from the Q values that have been learned for the two state action pairs. Again, this is false. Like we can recover for MDP, not from DP directly. And policies recovered from QMDP like solution methods are always better than the policy learned by history-based methods. So again, this we cannot say that it will always happen. Might happen, might not also. Again, none of the above cannot be the answer. I hope there is no doubt in this. Now let's move to the second question. So consider the below grid world. In the figure above, black squares are blocked. So black are obstacles these like cells we cannot, the agent cannot be inside these cells. And assume that the agents can see one step in the four cardinal directions. So this is like you can say north, south, east, west, or simultaneously you can say up, down, and east is right, west is left. Assume that, so basically like this means that you see in only the four cardinal directions, not diagonally. So diagonally you don't see. That is not allowed. Assume that agent's observations are always correct. So this again means there is no noise, right? And there is no prior information regarding the states. So no prior information is given regarding the states. So what is the question now? So if the observation is that there are no obstruction to the east or west, but they are present to the north and south. So it is saying that there are no obstruction in east and west. So you must be knowing this cardinal direction. North is this, south is this, east is on the right, and west is on the left. So they are saying that if there are no obstruction to the east or west, so horizontally there is no obstruction, and but are present to the north and south. So vertically there are obstruction both ways. The belief that the agent is in green shaded square is 0.5. So is it like that the belief that the agent is in green shaded square is 0.5? So this is one cell, right? In this slide, there is blockade on south, there is blockade on north. Even the wall is also considered as obstacle, right? So this wall is also an obstacle. So there is, but on east and west, like there is no, like for this, there is no blockade. So this is true. Like one cell satisfies this. So green cell satisfies the property, right? But what about the blue cell? Blue cell also satisfies this property, right? There is obstacle in north, obstacle in south, but no obstacle in east, no obstacle in west. So blue also satisfies this property. But they are saying that are these the only two cells? So maybe if you look carefully, this is also the cell which satisfies this property, right? In north, there is an obstacle. In south, there is an obstacle. But in east and in west, there is no obstacle. So this cell also satisfies this property. But their assertion is that the belief that the agent is in the green shaded square is 0.5. Should it be 0.5 or it should not be 0.5 because we are able to find one more cell. So you this is simply a counter example, right? There could be more cells, so you can check, but definitely it's not 0.5. It will be less than 0.5. If the cell we deduced is the only one, then it will be 0.33. If there is some more cell, then it will be less than that. So this is false. Only the green and blue shaded squares have obstructions to the north and south, but not to the east and west. So again, this statement is also false because we already found a square which has obstruction to north and south, but not east and west, and it's not one of these, green or blue. So this is also false. So this means that the assertion and reason both are false. So in this way, like you will have to analyze the cells. So there might be problems like this in exams also. Now let's move to the third question. So the third question says, consider the grid shown below. Walls and obstacles are colored gray. Okay, so wall is also an obstacle. There is some noise. I'll unmute. I think he left. To consider a grid world shown below. Walls and obstacles are colored gray. So these four cells are the obstacles. And also this wall is also an obstacle. Now, An agent is dropped into one of the unoccupied cells. So unoccupied cells we have five, right? These white ones uniformly at random. So this means like the agent getting dropped in any of these five cells, the probability will be 0.2. Right? The agent is equipped with a sensor that can detect the presence of walls or obstacles to its north, south, east, and west. So four cardinal directions, it can detect the presence of walls or obstacles. And that two immediate ones. So it cannot detect like this one cannot detect an obstacle like one step further. Immediate one it can detect. Uh, okay. However, the sensor is noisy. Okay, so they have given that the sensor is noisy and an observation made in each direction may be wrong with the probability of 0.1. So with probability 0.1, the observation in each direction can be wrong. That means like with zero point 0.9, it will be correct. So given that the agent senses no obstacles in any direction, so it has been given that the agent senses no obstacle in any direction. What is the probability that it was dropped in the cell marked X? Okay, so this is what we have to find out. So I hope like you guys are aware with the base rule in probability. So like first define the events. So A be the event that the agent is dropped in cell marked X. Okay, middle cell. And we event we like no obstacles observed. So these are two events. But what they are asking is they are saying that given that agent senses no obstacle in any direction, so B is given to us, and based on B that given condition, we have to see find the probability that it was dropped into the cell path X. So basically, what we have to find is conditional probability. The probability of A given B, right? And if you might remember this place rule from high school mathematics, and this will open up to be A intersection B upon probability of B. Then you can expand this again, and it will become probability of B given A, probability of A upon probability of B. And you can like expand this also PB. PB can be expanded as so probability of V given A, probability of A plus probability of B given minus C. Like negation of A and probability of negation of A. So this means negation. So basically like this term numerator will be like first term of the denominator. So we have to apply this base rule to get the answer. So now first of all, like let's see this probability of A event. A says that agent is dropped in the cell marked X. So first component in our numerator will be 0.2 itself because they mentioned that it's dropped uniformly at random, right? So in this cell, it's dropped uniformly at random. And again, it's saying that it doesn't observe any obstacles. So what is the probability that if it's dropped in this cell X and it doesn't observe any obstacle in any of the direction? So that probability will be like basically it means that there are no obstacles in any of the directions. So just the probability that the sensor reads correctly, right? If the sensor reads correctly in all four directions, then it won't detect any obstacle in any of the direction. So that probability will be for one direction it's zero point 0.9, and so we will multiply zero point 0.9 by 0.9. This we will do it four times. So it will become 0.9 into 4 because these are independent events. So we can multiply all the cardinal events, the cardinal directions we can consider as independent. So you can multiply this probability. So again, like I mentioned before, the numerator, like this first term will be here again, 0.2 plus another term. So what what is the probability that it's not dropped in this one, right? Cell mark that. So with 0.8 probability, it could be dropped in like the other four cells, like this one, or this one, or this one, or this one. So these four cells, it can be dropped with 0.8 probability. Now, once it's dropped in 0.8 probability, now we have to find out what is the probability that it detects no obstacle. So for if we consider this cell, so you can see that it already has obstacle in three directions. So in three directions, it should sense wrong, right? The sensor should give wrong reading that it has no obstacle. Although it has obstacle, so the sensor should say that there are no obstacle. And this should happen for all these four cells because for these are symmetric. So in this cell also, like there are three obstacles in three directions, but the sensor should give wrong readings in these three. And the remaining one, it should give the correct reading also. That is also a priority because otherwise, like maybe if we don't consider that, then it might consider a obstacle here. So what we have to ensure is that three directions, it should give the wrong one, and one direction, it should give the correct one. And this should happen for all four because we have already discussed these two, and these two will be symmetric. So that probability will come out to be zero point 0.9 like correct in one direction, and in three direction it should be incorrect, right? So this is the probability, right? So this we can solve. So uh, everywhere like five numbers are getting multiplied, right? So you can write this simply as 9 into 2, 9 raised to power 4 into 2, 9 raised to power 4 into 2 plus 9 into 8. Again, you can cancel 9. So this becomes 3. Again, this becomes 3. And you can cancel 2 also. So 2, 2, and this becomes 4. So what we have left is 9 cube upon 9 cube plus 4, right? And what is 9 cube? So 9, 9, 81, and 81 into 9, 729, right? 729 upon 729 plus 4. It comes out to 729 upon 733, right? So let's write the options. So 729 upon 733. So this I think we cannot reduce it even further. 7 plus 3, 10, 30. No, cannot reduce it further. So 1 by 5 definitely not the answer. 82 by 91, no. 164 by 72.73, no. Again, so these are like, mm, yeah, it should be none of the above. So I hope like there is no doubt in this because like these type of questions might be there in exams. So you should be prepared with your probability formulas and also linear algebra. There might be some basic requirement of that in solving the questions. Okay, now let's move to the second environment. Second, like this fourth question. Okay, it's the same environment. So in the same environment as question 3, what is the probability that the agent was not dropped onto the cell marked X? So in this case, we can consider event as AS agent not dropped in cell marked X. Okay, and if the observation made is that there are obstacles present only to the north and to the south. Okay, so B event can be obstacles only in north and northwest and south. So in east and west, there are no obstacles. So what is the probability that the agent was not dropped onto the cell matrix if the observation made is that there are obstacles present to the north and south? So again, same problem, probability of A given B, because this is the observation that you have made. So this is something given to you. Based on this given, you have to calculate the probability that the agent was not brought to the cell marked X. So again, like we'll use the same base formula. which is probability of A intersection B or probability of B. Then you can write this again as P is probability of B given A, probability of A upon probability of B. Okay, so let's do this. So final formula will be probability of B given A, probability of A. This I am writing for reference. Probability of B given A, probability of A plus probability of B given negation of A, probability of negation of A. Okay, so this is the event. So what according to our definition, the event is that a probability of A basically A is the event that it's not dropped in cell marked X, right? So what will be this probability? This probability will be 0.8, right? But we'll have to do for all the four cells because like here like symmetry is not involved. So we will have to see for all the cells, like four cells. So here like suppose if we are in this cell, then we have to calculate the probability that there are obstacles only to the north and south, right? Obstacle should be only on the north and south, not on east and west. So how can this happen in this case? So this can happen. So this should be correct, right? Because it's already there and obstacle is already there. So north should be correct, but and south should be wrong, and east and west should also be wrong, right? Because there are obstacles there. So it will be essentially 0.1 q, right? And into 3 should be wrong and 1 should be correct. So this is for this one. Now, uh, is there something in chat? Okay, let's see. Chat. Okay, so more people are joining. Okay. So either way, like so let's see like for this one. So this one also like east and west, there are obstacles, but the requirement is that in east and west we should not be having any obstacles. But in south, like there is already an obstacle and we want that. But in north also it should give wrong. So for these two cells, it's like this should be the probability. This will be probability B given A into 0.9. So you can multiply this by 0.2 and this also by 0.2 because that is the probability. And you can sum them up, then it becomes zero point 0.4. But let's see for these cells. So for these cells, like we actually want this north south obstacle we want it, but this east obstacle we don't want it to be free. Like we okay, sorry. So in east we want it to be free, but in west also we want it to be free. But in west there is an obstacle. So this one should be wrong. Right, this one should be wrong, but other three are fine. So this is fine, this is fine, this is fine. So for and similarly for this cell, so in east there is an obstacle, but we don't want that obstacle, so 0.1 here. But in north and south, we want the obstacles. So again, like 3 should be correct. Like west already there is no obstacles. So 3 should be correct. That means zero point 0.9 q and into 0.1 and this will be multiplied by what? Into 0.4 because I am considering both of them together. So you can consider these two together. So 0.4. So this will be like some of these will be our numerator. So let's write the numerator first. So our numerator will be zero point 0.4 into zero point 0.1 into 0.9 cube plus zero point 0.4 into 0.1 cube into 0.9. So this is our numerator. And again, this same entity. Okay, there is some doubt. Let's see. So how to access previous year questions for this course? So when you are asking previous year questions, are you talking about assignments or like exam?
No, no, previous year, like that are asked in previous examination, or just the practice questions also.
See, in my session, like I have already been covering some practice questions. So, like practice assignment and assignment are already available to you. But apart from them, like there is this problem solving section in which like there are some problems which are not part of the assignment and problem assignment. So some practice problems you can get from here, but I'm not sure about like last year's questions will be available to you because I think like the exam of NPTEL is computer based. So I don't think like
Yes.
they will release the question paper.
Okay. Like, sir, do you have any like previous year
N-
questions which you can
No, no,
share
no,
or?
no. I only have access to that those things only which you all have access to. So the same
Okay.
like page I also have access to. Nothing much.
And like
So
from where we can practice some more questions, like which
yeah,
resource
so
you are following for extra questions. So,
problem solving like you can see like for each week like I have this problem solving section in like do you have the access to the recordings right on YouTube?
yes, 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 yes. I
So
have.
there, like you can go to this problem solving section, and there will be like maybe 5 or 6 problems which are like not part of assignment and problem assign like practice assignment. So you can refer to these, or otherwise, like the standard thing you can do is you can just refer to Sutton and Bartow book, and there are exercises and examples also in that chapter. So you can refer to them also.
Okay.
So these are the two resources which you can refer.
Yeah. Okay. Also, sir, one more thing is
Mhm.
like I am looking for the questions that are relevant to examination, like the questions that will be asked in examination. So
Right.
like practice assignment I have done, but like obviously if I do some more questions, so I will be better prepared for examination. That's why this time asking.
Oh, okay. So maybe like in that sense, questions from Sutton and Barto might not be there, but like better you practice these problem solving session questions because these are also from this course itself, right?
Okay, I will watch
So
the previous lectures. Yeah, for that. Okay.
yeah, yeah. So maybe like some of the assignment questions, these used to be in previous assignments but got replaced. So that kind of thing. These are available on the website itself. So if you go to website of professor, and these are available. These problem
Sir,
solving questions.
can you share the link of the website?
Of website, just a minute, I'll share. Um, I'll show on browser. Uh, okay, so are you able to see this?
Yes, yes, yes.
So this is the website. So here, like you can find these problem solving questions, which are not like part of your assignment and practice assignment. So I'll paste this link in your chat, right?
Okay, okay. These I can consider as some extra questions, right?
Yeah, like these are more or less like similar to like what is asked in your assignment and practice assignment. So it's better if you practice these. These might help you in your exam.
Okay,
So, but
okay,
like
sure.
these questions are only MCQs. So, but I also saw that mail that there might be essay based questions. So for that, like you'll need to be ready. I'm not sure whether like they just wrote it or whether there will actually be essay type questions. Because if it's computer based, then how will you write the essay? Like you will not type
I
in a
think
box
essay
or
will not be there, I guess. Sir, I think
so
essay will not be there. Like,
it's like MCQ only.
I guess MCQ, multiple select, and I think integer type questions, like the one
Integer
given
type.
in assignment.
Okay, okay, yeah, yeah. So, so I think that, like this should help.
Okay. Like, sir, do you know
So
the exact pattern? Because like they have not released the exact number of questions or exact pattern of examination.
no, no, like this is the first time I'm also doing it, and I think like they won't reveal it. Like it will be revealed to you just like 2 minutes before your exam. So when you get the question paper.
Okay, okay. Also, sir, like I think in the at the beginning of this course, like I think I have asked you about notes and like if you remember,
Mhm.
reinforcement learning notes
Like,
and all. So do you have that thing? Like, do you have arranged that? Like,
like what? I didn't get you.
like at the beginning, I joined the sessions of yours. Then I didn't get the time, so I like talked to you about the notes of reinforcement learning, if you remember,
Uh,
right?
like what of reinforcement learning? I didn't get that word. What are you
It's
saying?
a reinforcement learning notes.
Notes. Okay, okay. So
Yeah.
notes, like I think I mentioned that time also. Like the thing is, you need to prepare your notes because, like, see, the thing is, with professor, like he's teaching on board, so there is
Yes.
no like slides. Otherwise, if there were slides, like they would have been made available to you. So there are no slides, but I have some notes like mine, but I can share them in the same Google Drive folder. But there might be like they are not thoroughly checked, and there might be like I haven't checked them for. There might be some typos. Obviously, conceptual errors won't be there, but the typing mistake and maybe like some notation. So
Yeah,
I'll
sir,
share
that
them
is
like
just
if it's
yeah, just
helpful.
I need for reference, just reference, like just to quickly see at a glance. If you can share that will be very helpful.
Yeah, yeah. So I'll share it like in the same like Google Drive folder. Probably by night, like around 9 p.m. Okay.
Yes, thank you, sir. Yeah.
Okay.
Also, sir, can you share your email or something so that I can contact you if I am in out after this
Uh,
session?
email like we are not allowed to share the email, so they have created that discussion forum, like where you can post your queries and they will see like I think like people from NPTEL like they keep a watch on those questions.
Okay, 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 sir. Yeah.
So you can find it in the Q&A session, like section of that page. So it will direct you to some Google group. There you can ask.
Okay, okay. Actually, there we will get the reply late or like we will not get the reply. Like these things happen there. So
Yeah, that is an issue. Like, but
yeah.
like we're not supposed to like make emails and everything like public. So
Okay.
that's
Okay,
not
then just
possible.
yeah.
Yeah.
Okay, okay. No.
Okay, then I'll go back to the slides again. So we have this numerator, right? We have the numerator ready, and same numerator will come here as first term into 0.1 into 0.9 cube plus 0.4 into 0.1 cube into 0.9 only 9. Okay, cube is it. But plus there will be another term. So it says that there should be a probability of not A. So in our this question, like our event is agent is not locked in the cell marked X. So not A will be agent is locked in the cell marked X. And that probability will be 0.2, right? So plus 0.2. And if it's not dropped in, like it's basically negative. So if it's dropped in X, then what is the probability that it will have obstacles only to north and south, not in east and west? So let's observe cell X first. So cell X, like it doesn't have any obstacles. So basically what we want is the probability that there is a obstacle in north and an obstacle in south, but no obstacle in east and west. So basically what we can do is we want two of them to be wrong, and but remaining two should be correct. So the probability of this will be zero point 0.9 square into zero point 0.1 square. So this will be multiplied by zero point 0.9 square into zero point 0.1 square. Okay. So again, like you'll have to just solve this and let's see. So again, like multiply by 1 lakh numerator and denominator works. So it will become 4 into 1 into 9 cube plus 4 into 1 cube is simply 1 into 9 upon same in denominator 4 into 1 into 9 cube plus 4 into 9 plus and this will become 2 into 9 square into 1. It's mechanical. So now what you can do is you can divide by 2. Here it's gone. 2, here it's gone. 2 and 2. Also by 9, so this will become 1. This is also gone. And this will become square. This will become square. And this will be gone. So essentially what we will have left is 2 into 9 square, right? 2 into 9 square and plus 2 plus 2, just 2. And in see this entire thing will be numerator itself. So I can write numerator again. And secondly, like there will be one more term in denominator. So that will be this 2 is gone, but this square is gone plus 9. So essentially it's this term plus this term again plus 9. So let's write it. 2 into 9 square plus 2. Got this thing right. 2 into 9 square plus 2 and 2 into 9 square plus 2 and plus 9. So this is 81, 81 into 2, 162 plus 2, 164, 164 plus 9. So it's 173, right? 64 upon 170. So this is the answer. Now let's see. 164 upon 173. Yes, this is the answer. So this is the correct answer for this question. So if there is any doubt in any of these questions, you can ask me again. Okay, so please can you repeat again how did you calculate the numerator part? And this is in question number. Okay. So numerator part. Yeah, I'll explain again. So our uh, event A is that agent is not dropped in cell marked X. So basically, like they have mentioned that it can be dropped in only 5 cells. So if it's not dropped in cell marked X, that means it is dropped in the remaining 4 cells, which are these 4 cells, like this, and this. So these 4 cells. So using our base formula, we have this, right? So we have to calculate the numerator. So first thing will be probability that it's not dropped in like any of these cells. Like it's not dropped in cell marked X, so it will basically be any of these remaining 4 cells. Okay. So and then once it has been dropped in that remaining 4 cells, you have to calculate what is the probability of event B. So that will be probability of being like a probability that you have obstacles only in north and south and not in east and west. So let's see like all the 4 cells one by one again. So suppose this is the cell we are considering as of now. So what we want is like that there should be obstacle in north and south, but not in east and west. East and west there should not be obstacle, but north and south there should. But when we notice like in north there is already an obstacle, right? So this should be like the sensor should sense this correctly. So 0.9 plus, right? But east and west, there are obstacles and we don't want obstacles in east and west. So the sensor should basically sense them incorrectly. So both times, like both sides, you'll multiply one time, so it will be square. Because these are like independent events, so you can multiply the probabilities. And for south, so for south, we want an obstacle, but there is no obstacle. So again, this also we want it to be wrong. So again, multiply by 0.1. So it becomes zero point 0.9 into 0.1 cube. So zero point 0.9 into 0.1 cube. But this is the probability of V given, like you can consider this as A1%. And probability of A1 will be 0.2. So 0.2 into this entity. And similarly, like if you do for this one, it will be also same. So basically like you are summing these products. So 0.2 into 0.9 into 0.12 And again, like 0.2 into 0.9 into 0.1 cube. So basically, like you are multiplying this by 2. So I multiplied it like here. So I kept these entities in 0.1 cube into 0.9, and this becomes 0.4 for these two cells, this one and this one. So in this way, like I got the first term, zero point 0.4 into zero point 0.9 into zero point 0.1 cube. And similarly, like if you do for the other two cells, you can have this zero point 0.4. But other two cells, the situation is that north and south, we already have the obstacles. In east, like this one, for east, we don't have obstacle, but in west, there is an obstacle, but we don't want the obstacle in the west. So what we can do is this should be wrong, but other three are fine. So this will be zero point 0.9 cube into 0.1. And similarly for this one also, because we want obstacles in north and south, but in east, like there is an obstacle, so we have to get it wrong. So zero point 0.1 and remaining three should be fine. So zero point 0.9 cube. So this is the second term plus. You could have like written it like sum of four terms and with point 0.2, point 0.2, point 0.2, point 0.2. So I basically clubbed them isolated. So I hope like you got this. Yeah. So yeah. Okay. Fine. So now I'll move to the next question. So the last question is. Assumption reason in partially observable systems. Histories that include both the sequence of observations and sequence of actions are typically able to disambiguate the true state of the agent better than the histories that include only the sequence of observations. So basically, this is saying that if you have two kind of histories, one history is like this history, S1, S2, S3 kind of history. Suppose you are at state T, so your history will be till T minus 1. This is one history. And second history is they are saying that S1, A1, S2, A2, this kind of history. And it will be ST minus 1, AT minus 1. They are in ST. So they are saying that histories that include both sequences of observations and sequences of action, like they are talking about this history, are typically able to disambiguate the true state of an agent better than histories that include only the sequence of observation. This one. They are saying basically like that this history, action with actions, contain more information than this history. And that is true because like we already have the information about the state, but we get additional information about actions also. And that will help us in like disambiguating the true state of the agent. Maybe like sometimes what happens like if like the MDP is like this, suppose it's like this. And you start here, and if there is one more street here. So you were here in the beginning, but you could have stayed here itself, but you chose to go there. So this action will actually help. Like that the first action you took was this one. So this will actually help you in getting more information that you are possibly now in this state, not in this state. So action will actually help with more information. So the assertion is true. And the reason they gave is different sequences of actions can lead to different interpretations of the sequence of sensor operations. Yeah, again, this is also true. So different sequences of action. If like we would have action like you are staying in this, so it will lead to different interpretation that you might be still be in this state. So that is also true. So, but is this the correct explanation of the assertion? Yes, it is. Right? So both assertion and reason are true, and reason is the correct explanation of the assertion. Okay. So I'll probably get back to you in like 1 minute. There is someone on the door. So just a minute, I'll come back. Okay. So so in this way, like all these five questions, are you able to hear me, right?
Yes, sir. Yes, sir.
Okay, okay. Yeah, fine. So all the five questions of practice assignments are now done. So with this, like I'll move to problem solving. So again, like there will be questions which are not part of practice assignment, and it might be possible that these questions might be there in your exam. I'm not sure. Better practice these also. So first question says that in the partial observability example that we saw, so this is talking about the example of the class. There were some observations which uniquely identify the state of the environment. Suppose in a problem, no such observations exist. There are no observations which allow us to exactly determine the state of the environment. So no such observations are there. In such a problem, is it ever possible to be sure which state you are in, given only the sequence of observations? So this sequence of observation basically means history. So if you are given a history, can you be sure, ever sure? This means like even if it happens once, like it's fine. And is it ever possible? Like maybe in some special example, is it ever possible to be sure that which state? It's not saying that it's always possible. It's just saying that is it ever possible to be sure which state you are in, given only the sequence of observations? Yeah, like is possible, right? Suppose you are in uh, your MDP is like this, chain type of MDP. So one, two, and this is the only direction which you can go. And if your history says that initially you were in S1, S2, S3, S4, S5. Now, like they are saying that you have taken one more action. Now you should be in S6, right? You can determine this. So it is possible to be sure about this based on history. In fact, like if you are following a deterministic policy, you can be sure about that based on history because your deterministic policy will say if you are in some state S. So deterministic policy, what is it? It's a mapping from state to action side, right? So if you are in some state initially, like you'll know that initially you were in a state S1, then you took A1, and since the policy is A1 and the dynamics are like deterministic also, so you will like kind of go into S2. So in that way, like if you are following a deterministic policy and also the dynamics of the environment are also deterministic, means that transition probability will lead you to just one state, not many state. So then in that case, you can be sure. I hope there is no doubt in this. Okay, so let's move to the question two. So suppose that some of the actions that are available to an agent in a partially observable environment have non-deterministic outcomes. So remember last example I mentioned that they have deterministic outcomes, but here they are saying that they have non-deterministic outcomes. How would this impact the agent's ability to determine the state it is in? So it would make that determining the state easier, definitely not. It would make determining the state harder, yes. And how this will happen, suppose in the previous example, we were considering deterministic kind of thing. That suppose uh, if you take a right action, then you will go right. But non-deterministic outcomes means if you take right action, then maybe with probability 95, you will actually go to right. And with probability 0.05, you might stay in the same state. Suppose you can think like, suppose there is very strong wind in some environment and the robot wants to move forward. So if he has taken the action that he like put forward his right leg and he wants to move in forward direction, but the wind like kind of made him stay in the same state. So that environment is kind of non-deterministic. So there are non-deterministic outcomes there. So in that scenario, like it will be harder to determine the state, right? Because if we were having simple one probability, if you took the right action and you moved right, and then in that case, like it will be easier. If you were in some state and you took the right action, then you will be in the state which is to the right. But here, like you don't know, with 0.95 probability, you might be in right, but 0.05 you might still be here. So so this basically non-deterministic outcomes makes it hard. I hope like you got this. So with this, I'll move to the third question. So question 3 says that referring to the partial observability example considered in the lectures. Okay, so partial observability example, okay, you might remember this one. So it was like this. Although like these cells are not perfect, you can think like this or something like this. And we had like this. Here again, and how many were here? Okay. Oh, no, like these look unequal, but consider them as equal shaped cells. This is also, and how many were there? Okay, so this was the example, and this is like obstacle. Yes. Yes. So you cannot like don't cite these cells. And assuming that there is no noise in the sensor outputs, so zero noise. Is it true that all observation sequences of length 3 or more result in elimination of uncertainty regarding the position of the agent in the environment? So they are saying that if we consider history of 3 length, like the past 3 states where you were in, is it possible like that you can eliminate the uncertainty completely? Like you can be 100% sure in which state you are. Is it possible? So suppose if we consider history of this time, suppose you were in this state, you moved right, you moved left again, and you move right again, and you move left again. So if you knew initially, like let's say this, you might remember this notation. There was an encoding of state also. Okay, so it was in clockwise direction. So suppose if we consider maybe like this 1010. So one means like there is obstacle in north, zero means there is obstacle, there is no obstacle in east. And then south there is obstacle and west there is no obstacle. So basically like obstacles in north and south direction, but no obstacles in east and west. So this is the state which will be given to you. So suppose if you are giving four such like we get a sequence of like 3 or 4. Like we consider 3, 10101010. So this is the sequence which you are given as history. Can you be like sure like which state you are in based on this? It's three length history. Suppose it's 1010. This means like there is obstacle in north and south, but no not in east and west. So there this cell, maybe I'll use another color. You consider this cell. There is obstacle, wall is also an obstacle. So north and south there are obstacle. Also this cell also there is obstacle in north and south, but east and west there are no obstacle. So basically this means that you took some path here. Maybe like after that you went back or stayed there and here. Like based on these three, you cannot say like which cell you are in. Also, it might be possible that this might correspond to this, also this, because these also have obstacles in north and south, but not in east and west. So with three length history, you cannot eliminate the uncertainty. So that is not possible. So again, like the answer to this will be no, right? You cannot eliminate complete as like uncertainty completely using sequence observation sequences of light. So I hope like you got this. If there is any doubt, you can ask me. Otherwise, I'll move to the next question. To solve a commodity problem, suppose you decide to maintain belief states. Okay. Would the estimation of the belief states benefit from access to history of the observations and or actions? So they are saying that you are maintaining belief states. Would the estimation of the belief states benefit from access to history of observation? So basically, like history helps in like main MDP, but like they are saying like will it help in belief state updates also? So belief is basically updated simply by taking action, right? And you take some action, you are in some state, you take some action and you get to the next state. So basically what you have is you the action you took and the state you observe. So these are the two things that are available to you while you are updating the belief. And this basically makes it Markov belief update. So if it's Markov, like basically you are having access to action and what that action caused. Because like belief is updated based on like initially you will be having some belief for the previous step already. So based on the action you took in this after this belief, like how your belief will look like at suppose at time t it was some vector of belief will be there and suppose it was b then b dash at time t plus 1. So you already have this information. So additional history like won't help. Like you just need the current information and that should be enough for you. So this makes it not. So access to past observations or actions, will it improve? Will not improve, right? Because you are already maintaining the belief of last time step. You already have them. So what extra information will access to history will give? Nothing. Because you already have kind of incorporated that history in this previous steps belief. Because you are already updating this belief vector every time v0, v1, v2, and this belief vector over all states will be there. Won't help. I think there is something in chat. Okay, yeah. Fine. So now I'll move to the next question. Suppose that you are given a problem in which the agent is able to determine the state it transitions to after each action taken by the agent. Okay. However, the state space is described in a manner that requires the agent to consider information in the current as well as the latest past state in the state. Okay, to make decisions. Is the problem so refined and MDP? So it's definitely not an MDP because it's saying that apart from current state, suppose current state is ST, you will need the latest past state. So you need ST minus 1 also. So Markov property is violated here. So this is definitely not an MDP. You cannot say this is an MDP. Is it a POMDP? So what is the like main defining property of POMDP? There should be some partial observability, right? But that partial here they have given that the agent is able to determine the state it transitions to after each action taken by the agent. So there is no partial observability because it can determine it. So like they haven't mentioned it explicitly also that there is some partial observability. So we cannot say it's POMDP. So it's not a POMDP. So again, this is long, this is long. So can this problem be solved using RL techniques that we have studied, perhaps with possible modifications to the problem definition? So yeah, that we can do. So if you want to use RL techniques, so basically you will need an MDP. And how you can formulate an MDP is, suppose the states were like S1, S2, like ST minus 1 and ST. So what you can do is you can club these together and consider as one state. And next state will be S2, S3, and then S3, S4. So now this becomes Markov, right? Because like it doesn't have dependency on the previous one because these two are coupling together. So in this way, like by changing modifying the problem itself, we can solve it using other techniques. So this is not an MDP, not an POMDP also, but we can solve it using other techniques by just modifying it. So the answer is neither, but yes. Okay. So now with that, I'll move to the last question. So recall the example partially observable environment encountered in the lecture. So it is talking about this example only, this one. Suppose the goal in this problem is to reach the bottom right state with the usual -1 rewards for each transition. And assume that the agent starts 2 cells below the top left state. And the first action selected by the QMDP procedure is to move down. So basically they have given the goal state, which is the bottom right, and the start state also 2 cells below the top left state. Let's mark it. This is our goal, but the start state is 2 cells below the. So this is our start state. Right, this they have given, and the agent like moves downwards. This is the information which is given to us. The first action selected by the QMDP procedure is to move down. So assuming deterministic action outcomes with no noise in the observation. Okay, there is no noise in the observations, as well as the use of QMDP procedure where the underlying MDP has been correctly solved. So basically, they are saying that the MDP solution is optimal here. What can you say about the and there is no noise also. What can you say about the optimality of the agent's policy in this scenario? So suppose we were in this start state, right? And we moved down. Now we are in this state. Is this state uniquely identifiable? That is the main question which we should be answering. Because like this state, if we use this notation, we can say that there is an obstacle only on the west, right? So it will be 0, 0, 0, 1. Is there any more state like this? Like one more state like this, that there are no obstacle only on the west. So obstacle only on the west are this. But here obstacle is there in north also. Here obstacle in east, obstacle in east. Again, similarly, symmetrically, these two have obstacle in east, and this one has obstacle in south. So, and others like which can have obstacle in west are these ones, but this one doesn't have this one. Okay, but it has obstacle in east also. Again, this one also has obstacle in east. Similarly, this one also has obstacle in east, but this doesn't have obstacle in west. So this state is uniquely identifiable through this state definition. So if it's uniquely identifiable, then there's no uncertainty, right? And also they have mentioned that there is no noise in the observations. There is no noise also, like, and the state is also uniquely identified. So now using this, by solving this MDP, you got some policy 5 stars. And they are basically asking, if you have solved this MDP correctly, you have reached this 5 star policy. What can you say about the optimality of agent's policy in this scenario? So from DP scenario, what will happen with this 5 star? So the agent will follow an optimal policy to reach the goal. Yes, because like the state is uniquely identifiable. Once you are sure that you are in some state and that state is uniquely identified, so you are sure that you are in some state, and we also determine that state, that is 0, 0, 0, 1. So once you know for sure that you are 100% in this state, then you simply need to follow this policy by whatever it says and do it, and you'll reach the goal. So agent will follow an optimal policy to reach the goal. So this uniquely identifiable thing is important. Yeah, so with this, like, this is the last question of problem solving section. So if there is any doubt in question of practice assignment or that this problem solving section, you can ask me. Otherwise, I'll move to the demo. Okay, then I'll move to demo. Okay, so first demo which we so I won't spend much time in demos today, like because we are already at 7:10. So first demo, I'll give a brief overview. This is that like tiger problem. So tiger problem, it says that an agent is there and it's facing two closed doors. So there are two doors in front of the agent, and tiger is put with equal probability behind one of these two doors. So two doors are there, tiger left, named tiger left and tiger right. And the tiger can be with equal probability 0.5 behind any of the two doors. And the other door will have the treasure. So these are the two states. Basically, this mentions that there are two states, and the possible actions are listen for tiger noises. So you can either listen to tiger noises or open a door, either open left or open right. So there are three actions for you. And listening is not free. Like if you choose to do this listen action, then you will get a reward of -1. Otherwise, like what's the point? You can simply keep on listening until you are sure. So listening is should not be free. So it is having a reward of -1. Also, it is not accurate. So there is like 15%. This is typo. It means 15% probability that the agent hears the tiger behind the left door while it is actually behind the right door and vice versa. So basically, they are saying if you do this listen action, then with 0.85 probability, you can be sure about the door of the tiger, like behind which door the tiger is. Otherwise, like with 15% probability, if it's in left, you will hear that it's on right. If it's in right, you will hear that it's on left. So that 15% noise is there. And if the agent opens door with the tiger, so if you do this action, suppose open left, and the tiger is actually behind the left, then you will get a negative reward of -100. But if it opens the door with the treasure, then it will receive a positive reward of 10. And here, like this is slightly asymmetric because like if you open the door with the tiger, it can kill you. So basically, like a very high negative reward is there. But treasure will be like not that good compared to your life. So in this way, like small positive reward, plus 10. And after a door is opened, the problem is reset. So basically, they are saying that once you open the door, the problem is like the episode ends basically. The tiger is randomly assigned to a door with chance 50-50, and the agent gets another try. So this episode ends, new episode starts. So this is the problem which is considered. So now this is the demo. So I'll go quickly. So this is the all these demos are from the internet itself. So these are simple imports. So we have two states, right? Tiger left, tiger right, that we have already seen. And actions are three: open left, open right, and listen. And observations are observe tiger left and observe tiger right. So this is where partial observability come in because you can listen, but you're not sure like where the tiger actually is. So that is the partial observability because in if you it was completely observable, then you would have definitely known that behind which door the tiger is. But the door itself is causing observability issue because you cannot see behind what is behind the door. So that partial observability is there. And initial belief you can have like 0.5, 0.5 because like it's equally probable to be behind each of those in the beginning. And then gamma discount factor, you can play with this discount factor later also. I'll be sharing these tokens. And time horizon. So either way, like the agent can choose to simply do listen, 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 listen. So you need to terminate it apart from the usual termination by opening the door. So we will have this horizon as 5. So if within 5 steps you don't open the door, the episode will terminate. So again, these are the transition probabilities. So these are the initial transition probabilities. So suppose tiger left to tiger left state. So and these are like corresponding to three actions. So if you actually do the open the left door, then with 0.5 probability, you will go to tiger left. And with like if you do the right, then with 0.5 probability, you will go to tiger left. But if you are in tiger left and you do the listen action, then with one probability, you will remain in tiger left state only. And similarly, in a reverse manner, like here, like this probability will be flipped 0, because if you are in tiger left and you are listening, you are not moving to tiger right state. So, and in a symmetric manner, like this will happen for tiger right to tiger left and tiger right to tiger right. So these are the observation probabilities. Here that probability come in, like partial. You remember, like with 0.85 probability, you can be sure that tiger is behind the actual. So if you with 0.5, you can say that if it was behind the left, you heard the noises correctly. Otherwise, with 0.5, it might be on left, and you say it's on right. So that kind of probability is captured here. So these are like corresponding, each row is corresponding to one action. And this is like corresponding to, this is the first state and this is the next state. So in this way, like probabilities are stored, and this is the transition probabilities. Like this is corresponding to the usual MDP and this is corresponding to POMDP, observation probabilities. And reward, like as usual, -100 if you guessed it incorrectly, and 10 if you open the door of the reward, and -1 if you choose to listen. And similarly here. So this is the class definition, simple init function, which will like basically initialize all your variables, horizon, state, section, observations, initial belief, all these like we have defined before. Like gamma, transition metrics, observation metrics, and reward function. So all this we have already defined above, and function to update belief. So this is the like main thing which I wanted to show here. Like you can update the belief in this way. So for each state, we'll uh, so here like although like there are only two states, but what we are getting is action and observation. Remember one question we saw that we need only the action and observation, and this B means like this is the previous belief, like at time step t minus one. Suppose you are now updating for time step t, and what was the previous belief? So on the basis of that, you can update. So this is like you'll like iterate over the states, and you'll get that probability of observation from this matrix, because this matrix is already stored like in this unit. So you get that from self, and then you are like kind of doing this. And this is kind of weighted summing by belief. So in this way, you get this and you store this. And also like a new belief, like sometimes what might happen, like the new belief updates might be the probabilities might be that they don't sum to one. So in that case, you can normalize them by basically the sum. So divide by the sum of all the like events, like all the states beliefs, then it will become a simplex. So it will be a like everything between 0 and 1 and summing to 1 also. So that thing is happening here, normalizing. And this is the usual value equation algorithm. So we can use, you could have used policy equation also. So you can apply that. But the only difference will be like this belief will come here. So this is the usual pulse value equation, and then like we are printing it. So this is the like, so this was only the definition. Here we have made an instance of it and passed these parameters. So this will initialize everything, and then you are calling this value function. So once that is called, like all these outputs will be printed, and in the end I'll show you. So this is the reward list. So there is a reward list also. So initially like it's empty, and as and when like we get some reward, we are appending the reward in this. So what I am doing is I am basically printing the initial reward which I got at 0th step, and initially we were getting reward of -45. First episode we got -45 reward, and then like this is -45 because it's not one step, right? So it could be like minus some kind of that thing. So and at the last, after training, like after this value equation thing has converged, you can see that the last episode reward is -0.99. So this is, you can think -1. So -1 is quite small compared to -45. So in this way, you can say that it has kind of learned value equation. So this is one demo. So I hope there is no doubt in this one. In a way, like I won't go in detail because POMDB wasn't covered in great detail either way. So this is the like second demo. So second demo again, like this considers grid world. So in grid world, like if you are, it's like if you are moving forward. So this is similar to the example which I told you some time back. that there is a strong wind. So if you want to take direction in forward direction, then with 0.8 probability you will actually move forward. Otherwise, with 0.2 probability you might stay at the same place. And if you are trying to move sideways, like forward and backward are like depends on where you are standing. If you are facing north and you are moving towards north or moving towards south, then with 0.8 probability you will actually move. With zero point 0.2 you will remain at the same place. But if you are facing north and or south and you are trying to move sideways, which means east and west, then in that case with zero point 0.9 probability you will actually move to east and west, and with zero point 0.1 probability you will stay the same place. And similarly, based on orientation, if you are facing east, then with zero point 0.8 probability, in that way, like you are moving forward means you are moving towards east still. So there, like with zero point 0.8 probability, you will actually move to east. Otherwise, with zero point 0.2, you will remain at the same place. And in this case, sideways will be north and south. So this is the like definition. These are the default parameters. So you can initialize a grade like 25, like 15 rows, 25 column, gamma, discount factor, epsilon is the exploration bonus, like exploration factor with 0.1 probability. So we are following an epsilon greedy. Alpha is the learning rate, number of actions, 4 up, down, left, right, or you can say north, south, west, east. Start state is 0, comma 0, then full state is basically the other corner 14, comma 24 because we are equating from 0. So it will be 14 here and 24 here. So n minus 1, and these are the obstacles. So you can play around with obstacles also. Just make sure that the obstacles are such that agent can actually reach. It should not be that the obstacles have completely blocked the agent. It can never reach goal state. So you have to design the obstacles carefully. And again, max one's maximum number of episodes. So we have kept that also 100. And initially we are empty. So this is the next state function. Next state function basically returns the next state and reward. So remember, like here we didn't use a standard environment. We like unlike card, pole, and tire, we are not having gym here. So we are actually defining our own environment. So here like that next state function is there. So you will pass the state and the action which you are taking, and it will return the next state and reward. So here like there are some if else kind of conditions. Like if you are already at the top and you want to move further north, basically you are on the wall. So you cannot move further north. So in that way, like this max will ensure that you will actually remain in the grid. And similarly for others also. And again, like if your next state is out of the grid, if you like basically collide with the wall, then you will get a reward of minus 100. And also if you collide in an obstacle, and also you will get a reward of minus 100. And if you reach the goals, there is a reward of plus 100. So this is the environment definition. So in this way, like you can define your own environment also. Need not like always use the environments provided by the gym. So this is the take action. So here, like as usual, epsilon greedy action selection with like epsilon, like if we generate a random number, if it's less than epsilon, we take randomly whatever action we this random returns, and otherwise like we will take greedy action. So this we have seen already many times, and this is the function to decide whether we should take action or not based on transition probabilities. So here, like we have to decide whether to take the action. Like this will epsilon greedy will actually suggest some action, right? But are we in a position to take that action or not? Like that is the what this function is doing. Remember, like that probability 0.8 probability. If you want to move forward, then with 0.8 probability you can move forward, but with remaining probability zero point 0.2, like you will stay at the same place. So this function is capturing that information. Okay, so this is like also like there is concept of orientation. You are already facing up and down, and action is up and down. Then like you are moving forward in this case. So with 0.8 probability, you will actually move. Otherwise, with remaining probability, you will stay at the same place. So this is will return 1 if you are like actually taking that action. 0 if you are not taking that action. You stay in the same. And similarly, like if your action is left and right, then we mentioned that sideways, its probability is 0.9. Then otherwise, like if orientation is like left and right, I mentioned this, like if you are up and down, then moving forward and backward means in north south. But if you are left and right, then moving forward will mean in east and west direction. So if it's up and down, then it's essentially sideways, right? So it's zero point 0.9 there. And if its orientation is left and right, and you are taking left and right only, then you are essentially moving forward and backward. Then probability will be 0 0.8. So with 0 0.8 probability, you will actually move forward, and with remaining 0.2 probability, you will basically remain in the same state. And this is the function to calculate the score. So you might remember this score equation from class. Like basically, we are weighting it by this belief values. So it is getting weighted here, and we are returning this. And this is the function to return observation probability. So basically, like there is partial observation, right? So you cannot observe everything in the grid. So that partial observability is captured here. So if you're like basically based on the current state and action, you will get the next state and then the reward also. And if your reward is minus 100, that means you have collided. So it will return zero, that and otherwise it will return one. So this is the only information which you have. So this basically returns observation probabilities. And function to the return transition probability. So this is the transition probability is corresponding to the actual MDP, and this is corresponding to the POMDP. And again, like similarly, if the agent is staying at same speed even after taking action, then with a 0.2 probability, otherwise like with 0 0.8, you are moving. And this is for sideways and this was for forward and back. So these are the transition probabilities also captured here, and if some state is valid or not. So check validity. Like validity means like you cannot be in obstacles. There will be some free cells. Also, initially you cannot be in goal state also. So goal state is also good because that is something which you should try to reach. Otherwise, you won't learn if it's already in goal state. And then like this is the function to these two are like the sigma transition is getting used here, but to update the belief. So this is getting called here. So basically, same belief update is happening here. So this is calculating the numerator and it's getting normalized here by this denominator. So we are not writing here. So in this way, belief is updated. And here, like this is the class definition only. So here we have created the instance of that class. Then initialize the Q value function. Initially all zeros. Orientation is also zero, run zero, counting steps. So here, like basically we can count like we have to reach the goal right from start state to a goal state, and we have to avoid the obstacles also. Also, like we need to reach the goal as fast as possible. So our proxy for good performance could be like to count the steps in like how many steps we are able to reach the goals. So that is like captured here, and like this is the running like for everything. So here, like we are starting initial belief at 0, 0. Since we are sure that this is always the start state, remember we defined start state as 0, 0 and end state as 1424. So that is the captured here. And again, like until you have not reached the goal state, you are increasing, you are taking action here. And here you are checking if that action can be taken. This means that like, remember that 0.8 probability. So if it returns that you can actually take that action, then you will move. And then you'll get the next state and reward. Otherwise, you will simply be staying in the same state, right? And then you are calculating these Q values, belief, then updating the belief using the functions we have defined above. And also that these are for the storing purpose, updating the Q value also. And here, like these will be weighted by beliefs. So that thing is there and orientation. So sometimes like after taking action, your orientation will change. So you need to change the orientation also. You will continue until you're like if your reward at any point which is plus 100. So in this example, there is no reward like minus 1 in between, right? So the point you reach 100, you basically you don't want to dilute this reward further. So you want to get this plus 100 as soon as possible. Remember that discount factor is there. Discount factor is basically diluting the reward. So in problems where we don't have -1 reward, we will have discount factor as 0.95. So this is diluted. Otherwise, if there was -1 reward, we could have simply kept it as 1. So we need to go as fast as possible so that this plus 100 doesn't get diluted and we are printing like so as you can see from this print it's also like gradually like initially number of steps taken is 15,000 like gradually like this number of steps should decrease. So as we can see now it's in hundreds and something. So it's 3 digit and let's see like gradually it becomes 3 digit. It means so it reduced from how many like almost in thousands to few hundreds. So basically means that we have learned enough and this is the graph which shows also that Like initially we were taking in thousands many steps, and gradually like we have done more, so we are taking lesser steps, or like in few hundreds. So that is captured here. Although it's not zero, but since the scale is much more, then like it's appearing that it's close to zero. So again, like with this also, like you can play around with parameters and everything, and as usual, you can try out stuff. So I'll share this also, and now we go back to the third demo, and this is about our favorite cardboard environment. And you might remember the action space and observation space. So remember, like other two problems, there was a component of partial observability. But in this cardboard problem, there is no partial observability. So what we can do is we can, like, these are the four observations. So what we will do is we will remove this observation, cart velocity and pole angular velocity. These two we will remove. And in this way, like two components will become unobserved. So there will be partial observability in that state. So this way we will do it. And rewards as usual, like we will have +1 for every step taken. We want to like balance the pole as long as possible. And these start state are assigned uniformly, and episode ends. We have already seen this before also. So all these things are there. Uh, So So again, like installations, you can do imports. So this is like CUDA. Here, like I haven't connected, but if you have GPU, then you can connect to GPU, and then this will run on GPU, not on CPU. So if you want speed, and you can run this on GPU. So here, like policy network, first like this demo basically does it in two ways. First, using like just normal neural networks, fully connected ones, and secondly, we will see like how using of LSTMs, because LSTMs are something which capture history well. So we'll see how performance improves with history, because this is partially observable. Although like Carpool is not partially observable, we have made it partially observable by hiding two of the observations. So this is the policy network, fully connected layer, like linear 2 into 64, then 64 into 128, and then finally 128 into 1, and value and sigmoid. So this way we define. First, like input X goes to fully connected layer 1, then value, you take value out of it, value on this, and then you pass this to fully connected layer 2, and again take value, then fully connected layer 3, and then sigmoid finally. And sigmoid, you might remember that it kind of returns probabilistic kind of thing. And then you are sampling, like using those probabilities. What is the uh, action which we should be taking? Okay. So this is the policy network, and similarly value network also. And this is the fully connected layer, fully connected linear. And here, like last layer, we won't have sigmoid or something because we want a real value. So we will have just fully connected layer. And these are the problem parameters. So here, like we are using gym environment, cardboard, policy network. So this device is basically like it will send everything to GPU if you have access. Otherwise, it will use CPU. And this is the optimizer for policy network. Adam as usual, learning rate. This is the learning rate value optimizer is also Adam with value parameters and learning rate. Gamma discount factor 0.99, step 0, episode reward list. And episode reward list is initially empty, but gradually we will append the rewards in this. And we are doing for 5,000 episodes. So here, like we are bringing that component of partial observability. So we are basically deleting the cart velocity and pole velocity. So basically, cart velocity was at first index. So first we delete it. So then remaining three indexes are there, 0, 1, 2. Then we delete for pole velocity. It's at index 2 now. So episode rewards. So also like we keep the horizon as 200. If it doesn't end, episode doesn't end in 200, then we will manually end it. And similarly, like here, like all those things are happening, you take that step function action, and then you get initial state, everything like episode reward is added, state equals to next state, and if done, everything like this we have already seen before. And again, like this is calculation of the return. This we have already seen before, like how to calculate return in using this reward function, and you are having this standard normalization here. And again, like similarly, you will have the all these updates of losses. all these like we have already seen before. So finally, what we have is like we can see like with episode, like episode reward initially. So here like the reward should be as high as possible. So we started off in double digits, and let's see like how we got. Like there are too many books here, so I'll directly go there. Still like if we don't use LSTM, like the reward is like this. And I also showed like a graph where like it fully got filled with these values. So again, like as usual, we will be taking running average here. So we took the running average of like 50 rewards, and that we have plotted. So this reward you can see, although it's increasing slightly, running average we got from 20, like average of 20 to around 55. You can say. Eventually it ended around 45 itself. So after 5,000 episodes, you can again play around with the episodes, number of episodes and everything. And then comes the LSTM thing. Like now we will be using LSTM. Let's see like with LSTM whether we are able to like get better performance than this 45, which we eventually ended with. So here like LSTM will come. So there we had fully connected layer, three fully connected layer. Here we will have LSTM. So LSTM is used to capture history-based dependencies, and again the forward function and select action function as before. So this is the policy network, and in value network also we will have a LSTM here. So that LSTM is there. Again the same environments, parameters, discount factors and everything, and similar kind of running. Only difference is that we are using LSTM here. So let's see the performance with LSP. So here again we started around 11:23 something, and let's see where we end. So this is like epochs. So see, you can see 3-digit rewards now. But in case of like normal neural network, we didn't see like non-LSTM ones. So again, taking the mean and plotting, now you can see like we are getting to an average around 120. So basically, this means that usage of some sequence kind of neural network which captures history, like LSTM or RNN. Like you can try out RNN also, LSTM or GRU also. So all those different neural networks are there, so you can try out them and also play around with parameters. So this demo basically shows that with LSTMs we are able to get better performance compared to neural networks, like simple neural networks, and also the epochs remain the same. 5,000 episodes only, like we got better performance. So this is the third demo which I'll be sharing. So also like all these are from the internet itself. We can play around with these. So now what I'll do is I'll go back to the slides. So I hope like the slides are visible now, right? Can someone confirm?
Yes, sir. Yes, sir.
Yeah, yeah. So okay, so now we'll do the questions of assignment. Although there are not many questions, only 5 questions in the assignment. But I'll also have to give a brief review of like lectures 7 to 12. So I'll do that fast either way because those lectures might be refresh in your memory since they are recent. So consider an environment in which an agent is dropped into either state S1 or S2 with equal probability. The agent can only view obstacles present immediately to its north, south, east, or west direction. So again, like cardinal directions only. North, south, east, and west. However, the observations made in each direction by the agent may be wrong. Okay, so there is noise. Theta probability 0.1. Okay, so if in state S1, obstacles are present to the north and south. So in state S1, there is an obstacle to north and south. And in S2, obstacles are present to the east and west. So in S2 state, obstacles are in east and west. Okay, what is the probability of the agent being in state S1 if the observation made is that there are obstacles present to the north and west? Okay, so again, like as usual, we will define the events first. So A is the event. What is the probability of the agent being in state S1? So agent present in S1, and V is the event that there are obstacles present in north and west. So obstacles north and west. So there is the these are the two events, and they are asking if the observation made is this one B. So basically B is given to us. Given B, what is the probability of it? So again, like the same base rule we will be using. So this time I'll write directly. So the expansion of base rule basically becomes probability of B given A, probability of A upon probability of B given A, probability of A plus probability of B given negation of A, right? Probability of negation of A. So what is the probability that of A event? So what is the A event itself? A event is agent is present in S1. Okay. And they have also mentioned that the agent is randomly dropped into either state S1 or S2 with equal probability. Okay, so probability of S1 is also 0.5 and probability of S2 is also 0.5. So we can write. So this is 0.5 probability of A. And not A means like if it's not in S1, then it must be in S2 because these two are the only two states. So this is also 0.5. Okay. So if you are already in state S1, then what's the probability that you have event B? So event B is that you observe obstacles to north and west. So north there is an obstacle and west there is an obstacle. So north there is already an obstacle, so north should be correct, right? So with zero point 0.9 probability, it should be correct. North. South, there is an obstacle, but we don't want it. So it should be 0.1. And west, we want an obstacle, but there is not an obstacle. So we want it to be wrong, right? So we want that. And east, it should be fine. Like there is no obstacle and we don't want obstacle also. So north and west, we want the obstacles. So it becomes 0.9 square into 0.1 square. So this is the probability of B given A. So this thing, so maybe I'll write it. So 0.5, this is probability of A into probability of B given A 0.9 square into 0.1 square. And again, same numerator will come here 0.5 into 0.9 square into 0.1 square plus this probability we know 0.5. So now let's see what is the probability of having an obstacle in north and west if we are in S2. So north, we want an obstacle, but there is not an obstacle. So it should be wrong, right? East, we don't want an obstacle, but there is an obstacle, again, it should be wrong. South, we don't want an obstacle and it's not there, so it should be correct. And west, we want an obstacle and it's there, so it should be correct. So this way we can get the probability. So this we have already seen many examples how to get this. So again, it will be 0.9 square into 0.1 square. So this thing is common everywhere, like 0.9 square, 0.1 square. So you can remove it. So it's essentially 0.5 upon 1, basically 5 upon 10, 1 upon 2. So 1 by 2 is the answer. So let's see. So 81 by 82 definitely not. Okay, 41 by 82 is 1 by 2. Right. So this is the answer. So, either way, for assignment, I shouldn't have given, but either way, like you need to be careful. You should not search just 1 by 2. It might be possible that one of the options might be reducing to 1 by 2. So you need to check that also. I mean, the others will be wrong here. So I hope like you got this. If there is any doubt, you can ask me. Otherwise, I'll move to the next question. So there was an exercise. Read a bit. So in the same environment as question 1, suppose S1 has obstacles present only to the north and south. Okay, the same thing. S2 has obstacle present only to the east and west. Okay, so S1 and S2 like they have same architecture. What is the probability of being in state S1? Again, like let's capture it. Is present in S2. If the and given is if the observation made is that there are obstacles present only to north, east, and west. So they have added east also. So B is right. Obstacle in north, east, and west. So this is the difference here. So again, the same base rule we will apply and let's see. So maybe I'll write on next slide. So probability of B given A, probability of A upon probability of B given A, probability of A plus probability of B given negation of A and probability of negation of A. So what is the probability? Like again, like this probability of state S1, this will be 0.5 here also. Because this is a continuation of last question itself. So those probability we can get in 0.5 and 0.5. Like this is S1 and this is S2. Now if we are in S1, and what is the probability that we see obstacle in north, east, and west? So S1 was like this, right? What was S1 like? S1. S1 had obstacle in north and south. S1 has obstacles in north and south. Why? So north, there is an obstacle and we want it. So zero point 0.9, right? East, there is no obstacle and we want an obstacle in east. So it should be 0.1. Okay. West, there is no obstacle, but we want an obstacle. So again, 0.1 here also. South, there is an obstacle, but we don't want obstacle in south. So it should be wrong here also. So this is the probability of numerator. We write this here. Maybe I'll write it again. 0.5 into 0.9 into 0.1 cube upon this numerator will come again here. 0.9 into 0.1 cube plus. Again, this thing is 0.5. Now we analyze this again. If you are in S2, let's do this. So S2 was like this. We had an obstacle in east and we have an obstacle in west. Okay. So what we want is obstacle in north, east, and west. So north there is no obstacle, but we want it. So north should be 0.1 long. Okay. And east we already and we want it. West also we have an obstacle, we want it. So 0.9 square. And south, we don't want an obstacle and it's not there. So it's 0.9 cube. So this is the probability there. Probability of B given not A. So let's write this down into 0.1 into 0.9 cube. This you can cancel. Okay, so again multiply by 10,000 numerator denominator, you get 9 upon this will be 9 again, same as numerator plus 9 cube. So 9 upon 9 plus 9 cube. So 9 upon 9 plus 9 cube. We can again cut 9. So 1 upon 1 plus 9 square. 1 upon 1 plus 81 equals to 1 upon 82. Now you can check if one of the option maybe it might reduce to 1 upon 82. If it's reducing, then fine, that will be the option. Otherwise, you have the option none of the above. So be careful, like some of the options might actually be none of the above. So now let's move to the question number 3. So one of the reasons that history-based methods are not feasible is because of the significant increase in the state space size when the trajectory is long. So this is true, right? We remember like if your history-based methods, like what happens? Suppose there are n states. right? This is the number of states. So firstly, at first step, you will have just n. Like this will be your like possibilities. But next, you will have like state and state, like state one and state two. So this will be essentially combination will be n square. Suppose this is s on this. Then third step, it will be s1, s2, and s3. So possible combinations will be n cube. Then S1, S2, S3, and S4. These are like time steps, the subscripts. So the possibilities will be N4. So in this way, you can see like it's not feasible because there is significant increase in the state space size and the trajectory is low too. So the number of states increase polynomially with respect to trajectory length. So trajectory length here is 1, 2, 3, 4. So you need to figure out whether it's increasing polynomially. So is it like increasing polynomially? Is it something like polynomial like x square or something? But no, like here the power itself is changing. So it's increasing exponentially, right? So again, this will be wrong. With this, you can get the answer. So I hope like there is no doubt in this one. There is, maybe I'll just check once. Okay, then I'll move to the next one. So in case of POMDPs, which of the following is a good estimate of the return of a trajectory of policy pi, given the current belief state and the solution to the underlying entity? So is it like average of all B pi where belief is positive? So this basically means you are giving equal importance to all the states which have positive belief. So equal importance we don't want to get, right? It should be weighted by beliefs. So weighted average of V pi s where Vs are the weights. Yeah, it should be the answer. Like it should be weighted by this belief. And this says that third option says that average of all V pi s where V pi belief of S is greater than equal to alpha. So this will basically mean that suppose if belief is this alpha is 0.2. If belief is more than 0.2, then you will be giving equal importance to all such states. And we don't want to give equal importance to all such states because it might be like some state might be having much higher belief. And also this means that whatever states have like less than 0.2, you don't give anything to them. That is also wrong. So again, this should not happen. So it should be like weighted average of like V pi of S where V is are the weights. And this we have already seen in class also. So consider the grid world shown below. This is the last question. Walls and obstacles are colored gray. Okay. So walls and obstacles, these are the obstacles. The agent is equipped with a sensor that can detect the presence of walls or obstacles immediately towards north, south, east, and west. So I think like you should be like very well versed with these cardinal direction questions because there are already many questions using these cardinal directions. So you should solve like these assignment questions and everything carefully. And also remember the base rule. So which of the following are true if we represent states by their sensor observations? So is the grid world first order Markov system, second order, third order, or fourth order Markov system? So basically we need to check whether like if each state is like uniquely identifiable. You can identify each state uniquely, then it will be first order. Otherwise, like if you need history, like maybe past two steps, then it will be second order. And if you need three steps, then it will be third order. If you need like four-step history, then it will be fourth order. So let's see, like if we can uniquely identify each of these states. So here we have obstacle in north. So by bar, I am implying that there is an obstacle. But is there an obstacle in south also? Is there an obstacle in west? Yes, so west is this direction. There is an obstacle in west also, but there is no obstacle in east. So this state can be represented using this. Now let's see for this state. Is there an obstacle in north? Yes. Is there an obstacle in south? No. Is there obstacle in east? Like first write west. West no obstacle, but there is obstacle in east. So again, these two are different. So these are uniquely identifiable. So similarly, we have to see. Yes, we have to see that all these states have different these patterns. If two states have same patterns, then we cannot say that it's first order marker. So let's see this one. So north, it's free. South, there is a obstacle. West, there is an obstacle. So white ones are the like valid states. You don't need to check for obstacles. And east also, there is an obstacle. So again, no clash till now. Like all of them are different. So let's see this one. So north, there is an obstacle, and south, there is no obstacle. West, there is an obstacle. East, there is an obstacle. Again, like this is different, right? Yeah, this is different. This is also different from this. So let's see this one. Is it like north three? So north is three. Again, like south, there is an obstacle. East is three, but west there is an obstacle. So again, north three is just this one. No clash with this one. These two are different. So till now, like five states are uniquely identifiable. Now let's see this next one. North, there is an obstacle. South, there is an obstacle. West, there is no obstacle. But east, there is an obstacle. So let's see. Goes with north and south obstacle. This is the only one. Again, it's different. So all the states are uniquely identified. Right. So if all the states are uniquely identifiable, then the great world is first order Markov system. Definitely. And one more thing you need to know is like if something is first order, then it means that it's second order also. Because either way, like the information that you need is captured in the current state itself. But if you provide any history, it's still fine. Like you can, if you can identify something with just one state, if you like can identify the state with just the current state, then if you provide something extra in form of history, then also you are able to identify with two also. So although like this is enough, but even if you provide extra information, still you will be able to identify it. So first implies second order, second implies third order also, and this implies fourth order also. So basically, it's like all four are correct. So also you can could have like guessed this from this multi-option correct. So this is also possible. So if you can deduce that a system is first order Markov system, then it's definitely second, third, and fourth also. When would it be second order? So yeah, so it will be second order because suppose you can already identify it with the current state. If you provide some extra information, second order Markov system basically definition is that with just two-step history, you can identify the system. You can identify the state uniquely. So if you can do it with just the current state and additional information, either way, like an additional information is not harmful. So you can identify with the current state itself. So with two also like some extra information, there's no harm. So it's two-step Markov also. In similar manner, you can extend the argument to third and fourth. Okay, I hope it's clear. So with this, like I'll move to the slides. Not slides. So this is the reading material. So again, like there are three blocks which I have linked. So this is the POMDP for dummies. So this is an old blog. So it's from 1999, 25 years ago, but still it's like one of the main blog which people read. So you can refer to this. And this is slightly new, but it's in C language. So you can read this POMDP.org. You can find tutorials and everything here also. Demos, code. So this is POMDP.org. And this is the video, YouTube video. So this is the video which sir was mentioning in the class that like a predictive state representation. So this is by Satinder Singh. You can go through this also if you have time. So these are the like reading material. And now with this like today's like week 12 session comes to an end, but maybe I'll briefly go through like the contents of week 7 to 12. So I'll open a Jamboard. I'll switch this. Okay, so I hope like you are able to see the browser. Someone confirm? Like, are you able to see the browser? Okay, I'll see in chat. Yeah, okay. So either way, like in last week, like we discussed still, like Monte Carlo of policy UCT and all. So after that, like we moved to week 7, where we introduce eligibility twists. So you can refer to these eligibility twists. Eligibility traces, and they were accumulating also, and there were replacing also. You can refer Dutch traces also. And after that, like there was an backward view and forward view, so you can refer to them also. And eligibility trace control. Then there was like a brief recap of Thomson sampling. So you got to know about maximum likelihood method and also Bayesian method. So all those methods you can go through. And finally, backward views there. So with this, I think lecture 7 was done. Now, from like till now, like till lecture 7, there was simply tabular approaches. Then we moved to function approximation. So function approximation, we can use neural network and parameterization. There is some loss of information, but there are some things which we gain, like we cannot use tabular approaches in large state spaces and large action spaces also. So and in continuous action spaces and continuous state spaces, like are issues. So we move to this function approximation domain, where we are you can use neural network, or there are other function approximators also, time encoders and everything. So you can see that like what the main focus of this lecture was on linear parameterization. So how to use like linear parameterization for function approximation, and there was state aggregation methods and function approximation, and like how do you use eligibility traces with function approximation. And then finally, like we saw some algorithms which you can see LSTD, LSTDQ, also LSPI, and finally, like the only model-based algorithm which was discussed in this course, which is fitted queue equation. So again, I think in week 9 also, like this fitted queue equation was again discussed. Also, like DQN was also discussed. So deep queue network. So these are like value-based methods. And then we move to policy gradient, because in continuous action spaces, these value-based methods have issues. Like I have already discussed why like value-based methods have issues, because suppose if we are having continuous actions, then either we'll have to have one node for each action, then infinite actions means like we cannot have infinite nodes. And if you pass like action as one of the input and get a continuous value, then basically that argmax operation will cause issue, because like you'll have to perform this argmax over all possible actions, and you will have to call this neural network many times, infinite number of times. So these were the limitation of value-based methods. So we move to policy gradient, then we discuss mean force also. So you can go through policy gradient methods also, and then we also mentioned that how the variance is too much due to trajectories and all. So we introduced like baseline subtraction, and then if the baseline is value function itself, then that becomes integrated methods. So this was lecture 9. From like till lecture 9, like it was proper reinforcement learning, then we moved to hierarchical reinforcement learning, and there we discussed like 3 different frameworks. Also like the architecture which was underlying was SMDP. So you can go through options and HAMS also like max q. So this was in lecture 12. So lecture 11. So and this was hierarchical reinforcement learning. And in lecture 11, like we have max q. So we saw a demo of max q also. So if you want more information, and I also linked some blogs and some papers of these algorithms in the reading material. So you can, if you are still having doubts, you can go through them because like these topics are not available in Shutter and Bartobo. And then finally we have like today's lecture, which is form keeping. Although like there are just two videos in that, but still like it's an important topic because like the questions which we have solved like actually required you to apply the space rule. And there might be similar questions with different values. So you should be familiar with this base rule also. Like in between also in some examples, we saw that basic concepts of mathematics like geometric, like you know this geometric progression GP series, like infinite sum of infinite GP. So all those basic mathematics concepts you should remember, like probability, linear algebra, arithmetic. So yeah, that's it. So with this, I'll end the session. So best of luck for your exam and thank you.
Thank you very much, sir. Had a great session, sir.
Yeah,
Practical programs are so great and your tips are so great. Problem
thank you.
explanation so great, sir. Wonderful, sir.
Right.
Have a,
Thank
have
you.
a great time,
Okay.
sir. Bye, sir.
Yeah, but okay. So with this, I'll stop the recording.